Here's a video for those of you that need a little push for the computer exercises for this week, specifically when you're dealing with calculating the upper bound of error in between a function and its Taylor series representation anchored at a particular point. So as a sample question, we're going to look here at the cube root function, and we're going to say we've built the third order Taylor polynomial for this function centered at x equals 1, and we're going to say, well, for any other values in between 0.5 and 1.5, if we used the third order Taylor polynomial to play the role of the actual function for points in that interval, what's the worst that we could do in terms of error? What would be the largest error we might expect? Here, as you've seen from the notes, is the formulation Taylor's inequality, which tells us specifically that. Now, this is a lot of alphabet soup, so let's break it down. First of all, remember that this r sub n that we're looking at is the remainder, which is the distance in between the value of the function itself, such as 1/3, and the Taylor polynomial, which has been constructed to play the role of that function in a particular interval. And we know the Taylor polynomial isn't going to match the function exactly except at the anchor point itself, but the whole purpose of developing these Taylor polynomials is to come up with something that isn't the function but behaves a whole lot like the function and provides very, very similar values within a given interval. This mess right here is the formula that tells us the largest value we would expect the remainder, the error, to take on in one of these intervals. The key to unlocking this formula is remembering what all the alphabet soup means. Okay, so first of all, n. Well, n is just the counter for the Taylor polynomial we're working with. In the question we're about to look at, we're building, or we're pretending we've built, the third order Taylor polynomial for this function. And so n would be 3. D is just a measure of the interval we're talking about. And so for the function we're about to consider, we're asking about the interval from 0.5 to 1.5. This is centered at x equals 1, and that means that the width of this interval in either direction is 0.5. M is the weirdo. This m is the upper bound of a derivative of the function on the interval that's in question. So again, the function we're about to tinker with is the cube root function. We're going to ask the question, how bad off could we be if we used the third order Taylor polynomial to estimate values for that function in this interval? And that means that we're going to have to come up with the fourth derivative of our function and learn something about it on our interval, specifically what's its upper bound, or what is an upper bound, meaning go find a number that's bigger than anything you see on this interval for that fourth derivative. Okay, so I'm going to take this sheet away for a second, and I'll put it back in if we need to. But here are some of the specifiers. The d value we're going to need to work with is 0.5. That comes from this interval. Again, it's centered at 1, and then we go half a unit in each direction, and d measures the hop in each direction that we go to complete the interval, and so that's 0.5. N is 3. We're looking at the third order Taylor polynomial. And so then, in order to complete the formula, and what the heck, I'll write it down one more time. Right? We're after this, the maximum size, magnitude of remainder between the Taylor polynomial and the function itself. And it comes from that mess. And notice that we already have a whole bunch of that all ready to go. Just by knowing our interval, and just by knowing that we're looking at n equals 3, we can already complete that denominator, and we can already complete this term to the right. So the only thing we're waiting for is this m thing. Okay, and remember, m is an upper bound that comes from the fourth derivative on the interval. And so our function is the cube root function. We need to go down to the fourth derivative. N plus 1 is 4. We need to go to the fourth derivative, and whatever that looks like. And then we need to take the absolute value of that and find a cap, a numerical cap for that function. So in order to get that done, I'm going to hop over to Maple and have Maple help me with these calculations. So we are in the middle of a calculation which is going to ask for something kind of strange, and let's see if I can actually say this correctly. We are after the upper bound, or an upper bound, because there isn't just one, an upper bound on the absolute value of the fourth derivative of the function x to the 1/3 on the interval from 0.5 to 1.5. Now the reason we're after that is part of the other story that we'll get back to. But to calculate this, I've set up Maple to do some heavy lifting, and I've prepared a few things ahead of time, and you should know how to do most of these things. In this first line here, I've used the function defining gizmo, which comes from this left-hand column menu, to say, hey, I'm about to name a function whose name is f, the variable is x, and what's going to happen to x? Well, it's going to go to x to the 1/3. So we've defined f of x equals x to the 1/3. And then we need the fourth derivative of this thing. So I've borrowed the derivative widget, and I've superimposed some superscripts of 4 to go to the fourth derivative, and I'm specifying f of x specifically, and Maple now knows that f of x is the cube root function. That returns this expression, which is the fourth derivative of x to the 1/3. I know that I need to work with the absolute value of that, so here I'm asking for the absolute value of that expression. Instead of copying and pasting, though, I'm using Maple's line referencing, which you can call up with Control L, and this expression is referenced as line number 2, and so if I plop down an absolute value bar, then hit Control L, type the number 2, and then close those bars, I then get the absolute value of the function, the expression that was in line number 2. That's now line number 3, and in order to find an upper bound of this absolute value of the fourth derivative of the function x to the 1/3 on the interval from 0.5 to 1.5, I'm about to execute a plot command which says, hey, Maple, plot the expression sitting in line number 3 for the interval of x going from 0.5 to 1.5. And boom, there it is. This is a plot of that absolute value of the fourth derivative, etc., etc. And we are after an upper bound, which means we're after a number that's bigger than everything we see. And so, where do we find the highest values of this curve? Well, they're over here to the left. And it looks like, right, x equals 0.5 is this axis, and it looks like the function hits, based on this scaling, there's 11, there's 12, maybe 13. So let's say that, just by visual estimate, that 13 is an upper bound. An upper bound just means something is bigger than everything that you happen to see. And again, the interval from x equals 0.5 to x equals 1.5. This is the absolute value of the fourth derivative of our cube root function, and we're going to say that, hey, 13 is bigger than everything in here. And that will be our value. Now, we could also say that 5,000 is bigger than everything in here, but the way that this value is used in our calculation, we want it to kind of be as close as it can be to the actual values of the function. So, I'm going to go back to the pencil and paper now and carry this value of 13 back. Okay, we are back to the original calculation. Just as a reminder, here's what we're doing. We're handling the cube root function. We've pretended that we've found the third order Taylor polynomial for this function on the interval 0.5 to 1.5. And we're wondering, how bad off could we be if we used this third order Taylor polynomial to calculate a value rather than using the function itself? What is the maximum possible error? That is this value r, which is calculated by Taylor's inequality here. We preloaded some information just based on the interval and the fact that we're dealing with the third order Taylor polynomial, and then we had to go off on a goose chase to come up with m. And m, if you remember, I'm going to slide this paper in here one last time, is the upper bound of a certain derivative. In our case, it would be the fourth derivative, since n was 3, of our function on the interval that we're hunting through. And so we opened up Maple. We had Maple calculate this fourth derivative, find its absolute value, and plot it. We saw a plot that looked something like this. It looked like the largest value of that curve itself hit around 12, and so we're going to take 13 as an upper bound, meaning it's a number that's close to the action but is bigger than anything that we actually see. It's a cap, a lid, numerically, on the values in question. And now, just for fun, we're going to go back to Maple to not only calculate that value, but also take a look at what it actually means. All right, we're back in Maple, and I need to first of all calculate the value 13 over 4 factorial times 0.5 to the fourth. If you don't know what that represents, rewind a little bit in this video. That comes out to be 0.0338-ish, 0.0339. So one more time, that's what this number means is, let's say we started with the function x to the 1/3, the cube root function. We decided to build the third order Taylor polynomial for this function. And we're going to compare values between the function itself and the values that come back for this third order Taylor polynomial on the interval from 0.5 to 1.5. What's the worst error that we could come up with when we do that numerical calculation? Well, the answer is the worst error we would expect is about 0.034 if we want to round it to that. So let's tinker with a couple of values just to see what this means. So I'm going to pick, I don't know, something in the interval from 0.5 to 1.5, which isn't 1. The difference between the Taylor polynomial and the function at 1 itself should be 0, because that's what we designed as the anchor point. But anywhere other than 1, to the left or to the right, in between 0.5 and 1.5. So I'm going to take 0.8 as my magic point. And this round of Maple is still left over from what I just showed you a while ago. So it's got all this stuff already built in. So f has been formally assigned as the name of the function that's x to the 1/3. So when I have Maple calculate f of 0.8, I'm asking for the cube root of 0.8. It's 0.9283, etc., etc. Okay, what I want to do is calculate the third order Taylor polynomial for this function, evaluated at 0.8. And make sure that the value we get from that and this actual value from the function is no farther apart than 0.034. We want to compare this actual value of the cube root of 0.8 to what we would get from the third order Taylor polynomial for the function at x equals 0.8 and see how it compares. We don't want to do that from scratch though, right? Making Taylor series is kind of annoying. So what we're going to do is let the wizard do it. I'm showing you behind the scenes of Maple here. Maple has, under the Tools menu, various things called tutors and tasks. In tasks, you can go to Browse and look for Calculus, and then open the single variable stuff, and then hunt for Taylor approximations. I've already done that, and so it's sort of saved that particular task for me, so I'm just going to click on that, but you can hunt for it if you need to. And it's going to open up a whole big messy thing here. And what we can do is interface with this box to change the defaults. So our function happens to be x to the 1/3. The degree of Taylor polynomial that we are requesting is 3. Our base point is x equals 1. We can ask for the Taylor expansion, and we can ask for which is the Taylor polynomial plus the rest of the trailing terms that we would see, and the Taylor polynomial itself. And then what I can do is just cut out the Taylor polynomial. I'm doing Control C, and then I'm going to go below this window, And what I'm going to do is call up the function defining widget, but this time instead of letting it be named f, I'm going to call it capital T. I'm not going to worry about the subscript. The variable is x, and the result is paste the Taylor polynomial. So this is now the third order Taylor polynomial for cube root of x, named as the function t, and I'm going to ask for t of 0.8. Just like earlier, I'd asked for the actual functional value at 0.8. And we get 0.9283950618. Now it's hard to scroll up and down around all this stuff that's been put in there, so I'm now going to go back to the paper one more time and summarize this. The top of this sheet of paper should look familiar. This is where we started everything off with the original question, and now we're ready for the payoff. Before our last stint into Maple, we had named some parameters. We went to Maple the first time to calculate this weirdo value capital M. If you don't remember what that was, rewind the video. And we used those values of D and N and M to calculate this R sub n, or its absolute value. And again, that's the maximum error that we would expect between our function and our Taylor polynomial over the given interval. We went over to Maple and did some more manipulations, which you've just seen. And first of all, we just flat out did that calculation in Maple instead of pulling out a calculator, and we learned that the size of Rn is 0.0339, which means if we take any x value between 0.5 and 1.5, plug it into the actual function, plug it into the Taylor polynomial of order 3, the worst size of difference between those two values should be about 0.034. And we picked a point and tested it. So we went to 0.8. That's in between 0.5 and 1.5. Your test point cannot be the anchor point itself. We couldn't pick 1 because there the difference would be 0. That's the whole point. So we picked 0.8 instead. And f of 0.8, in other words, the actual cube root of 0.8, is 0.928318, etc. And then in Maple, we asked for the production of the third order Taylor polynomial. We got it, and we plugged in 0.8, and we got 0.928395. These two values should be no farther apart than this, because this value has been calculated as the biggest possible difference between these two numbers from within the interval. And if we actually run that difference, it turns into 0.00077. That's the difference between these two numbers, and that number is definitely less than the maximum error that was predicted by Taylor's inequality, and so it's all good. So far, it doesn't appear that anything went wrong. Now, why do we need to know the maximum error? Because sometimes in numerical calculations that you're going to do over and over and over, it's less numerically taxing to operate with the Taylor series or the Taylor polynomials than it is with the function itself. And so you want to have an insight into, well, how bad off can I throw my calculations if I do this? Or you can ask the reverse question and say, let's suppose that I can have an error no more than 0.0005. Well, then how many terms would I need in my Taylor polynomial to make sure that I stay within that maximum allowable error? That's what this sort of calculation can let you do as well.